episode or 3-minute videos for the channel. Today we will now solve another MAT question from 2010. This time it's question 1H. This is the 94th video of its kind. What's so special about 94? 94 is in the middle of a triplet of semi-primes. So 93 is 3 times 31, 94 is 2 times 47, 95 is 5 times 19. I can prove to you that every time there is a triplet of semi-prime, there is always one that is divisible by 3, one divisible by 2, and one divisible by 5. Though I will not prove it to you now because we have got this MAT question to wrangle. This MAT question gives us 4 statements about this equation. Let's start with statement 1. When n is equal to 3, let's draw it out. So 1, 2, 3. See, then question I is obviously false because this is a cubic, and you know what this means? All cubics either actually have rotational symmetry, which is not going to go our question now, but it's a good point to have. And the second point is all cubics have a real solution. It's quite difficult, right? But I have seen Cardano's formula, and they always be seeing a real solution or two. Now, let's start with statement 2. This n triple equal 0 mod 2 is actually where n is congruent to 0 mod 2, and it actually is just fancy mathematical language for saying that n is even. There is a real solution for all k. Question 2, statement 2 is false. Now let's draw it for n is 4. So 1, 2, 3, 4. This graph will go like this. And do you know what this means? This has 2 minima. Let's just drop the minima. And below this line, there is no real solution. So statements 1 and 2 are false. We're getting tired of going to numerical order, so let's go into statement 4. There's no repeat solution. Well, let me show that there is a repeat solution. As you can see here, we just drew this line here below the 2 minima, and it turns out that the minima are of the same height. So if we... Alright, let's just don't do the derivative, but look. Since there are 2 minima, then that means there must be a repeat solution. So that means if you transpose it up, it will look like this. See? 2 repeat solutions. In this case, these repeat solutions are actually double roots. And you know what this means? Statement 4 is false. And the same goes for odd numbers. So if the x-axis was here, there will be this single root here and there's a double root here. So there is a repeat solution. Huh? That's confusing, right? Anyway, k greater than 0, at least one real solution. That's right. Out of all the graphs being drawn, so let's draw a really crazy graph here. This is the graph for 1, 2, 3, 4, 5, 6, 7, 8, 9. n equals to 9. Isn't that a crazy graph right there? Anyway, I didn't draw it to scale, but you see here, if k is greater than or equal to 0, there is at least one real solution. In fact, there are 4 humps in this ray right here. Now let's draw for an even number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. n equals to 12. See? Even for large, odd, and even numbers, even when n equals to 2 times 10 to the power of 6 plus 1, or equal to 2 times 10 to the power of 10 to the power of 100 plus 1, this polynomial will be very interesting to draw, right? Well, it is. Well, is this some kind of mathematical joke? No. For every k, there is a real solution. Well, that's it for now. And these are some of the interesting properties about polynomials. And here's one thing about polynomials and me. Now I am trying to categorize all the polynomials. You know, factors, prime factors from numbers? Yes, prime factors. And this time, I'm now going to categorize all so-called prime polynomials. These polynomials cannot be split up into any simpler factor. Well, that's it. I hope you enjoy, and goodbye.